Hi, so in this lesson, we're going to continue verifying trigonometric identities. This is chapter 6, section 2, and this is day 2. We have 7 problems that we're going to work on here in verifying the identity. They're a little more complicated, a little more rigorous than the verifying trigonometric identities from day 1. All right, but we'll hang in there. All right, if you can't print out this note sheet, that's okay. I mean, you can just write the problems down as we go along. What you see at the top of my page here is a reference to page 497. That word is guidelines. I just realized when I looked at it that you might not be able to read it. All right, so on page 497 in your textbook, there's a set of guidelines, okay, right here, that kind of suggest to us how we should go about verifying trigonometric identities. Now, in the last video, I think I talked through most of these guidelines, but it's really good, especially when the problems get to be a little more complicated. It's good to have kind of a sense of how should I approach a problem, where should I enter, and if I get stuck, what else should I think about? So you might want to kind of look over this page and just remind yourself that, you know, if you're getting stuck in a problem, well, let me go back and look at these guidelines because maybe there's something there that I haven't thought about and about how to proceed with the problem I'm stuck on. Number 1 says work with one side of the equation at a time. It is often better to work with the more complicated side first. We did do that in the last lesson. Look for opportunities to factor an expression. Perhaps we might have to add fractions. We might have to square a binomial, distribute that means, or create a monomial denominator. If you want to create a monomial denominator, that just means that monomial means you just want one term in the denominator. 3 says, look for opportunities to use the fundamental identities. Well, that would be your formula sheet. Always pay attention to note which functions are in the final expression you want. Just always kind of keep your eyes on what answer you're looking for to help you kind of work through the problem. Sines and cosines pair up well, as do secants and tangents and cosecants and cotangents. Another suggestion is when the preceding guidelines do not help, try converting all terms to sines and cosines. I do that sometimes too. That seems to be a comfortable way for me to continue a problem. I think probably the most important thing is number 5, always try something. Even making an attempt that leads to a dead end provides insight. Okay, well said there. Okay, and no worries if you can't complete a problem, if you can't verify the identity, you know, consideration will be given towards what steps you've gotten to. All right, so let's take a look at our problems. Number 1, the more complicated side seems to be the fraction, the left side of the equation. So it's the structure of this fraction is that we do have a monomial in the denominator. Look at tangent x times cotangent of y. Paying attention to x here and y here, paying attention to that this is a product. There's no plus or minus down here. This is a monomial or one term. Okay, so gosh, when I look at this, I mean, I could change to sines and cosines. That might be a little cumbersome. What else can I do? Well, the break apart method, or some of you learned it as the share the love step or strategy, may be helpful here, meaning this. Let's take this first term of the numerator and put it over the monomial in the denominator. Then I'm going to go to a plus sign right here. So we're sharing the love, if you will. Take cotangent of y on top, putting it over that same monomial denominator. Well, will this help? Well, let's see if breaking apart helps. Now, let's simplify each of these fractions since we broke it apart. Tangent of x and tangent of x. So thank goodness these are both x's, because if they weren't, I wouldn't be able to divide out the tangent of x. So I'm left with 1 over cotangent y. Let me leave this term for a minute and come over here. Notice you have cotangent of y and cotangent of y here. They divide out. And I'm left with 1 over tangent of x. Take a peek back up. Remind yourself what you're looking for. You're looking for tangent of y plus cotangent of x. Well, I'm looking at 1 over cotangent of y, thinking about my, my reciprocal identities. This could be changed to tangent of y. Oh, score. That's what this is. Now I'm looking at 1 over tangent of x, which is equivalent to cotangent of x, scored even further, and I'm done. So the takeaway from this was identify a monomial in the denominator. You had multiple terms in the numerator. Think about the break apart strategy. Sometimes I use that break apart strategy and I don't get anywhere. And unfortunately, I have to do a lot of erasing and start all over. Okay, observe number 2. The more complicated side appears to be the left side, so I want to transform the left side or work on it till I get cotangent of theta. All right? Well, looking at and observing what I have here, this side of the equation almost suggests algebraically that maybe I should FOIL, distribute. That's what I'm going to do. Let's FOIL. Don't forget the theta, it belongs there. You don't want secant without an angle. So when I multiply secant theta times cosecant theta, it appears like this. Outside terms, inside product, and then the last. At this point, that doesn't even look like it's going to be cotangent of theta. Start to look at your formula sheet, see if there's any kind of substitutions or anything. For me, when I look at this, I'm thinking I'm going to change whatever I need to sines and cosines. So let's look at each of these terms. I'm going to look at this term. I'm going to change secant of theta to 1 over cosine theta times cosecant will change to 1 over sine theta. I'll come back and multiply these two together in a minute. Plus, this term is 1 over cosine theta minus, all right, I got another product here. So that's sine theta over cosine theta times cosecant theta is going to change to 1 over sine theta. And then here, I've got another sine theta over cosine theta. Let's do a little cleanup, see if we can see anything, see if this is going to help us, or maybe we need to abandon this. Remember, these two fractions are being multiplied, so I'm going to have 1 over cosine theta times sine theta. That's the cleanup here. Plus 1 over cosine theta. Goodness. From here. Now right here, before I get to this subtraction, I see that the sine thetas will divide out, leaving me with minus 1 over cosine theta. And then here I have the minus sine theta over cosine theta. You may have observed that these are identical opposite terms, so they cancel. Okay, now what I'm left with are these two terms. Don't forget to extend that fraction bar. All right, well, I have two fractions and I have unlike denominators, so let's get a like denominator and see if that helps. Meaning I would have to come over here into this fraction, multiply by sine theta over sine theta. Remember, I want to try and get rid of a fraction, so maybe getting a common denominator will help. So what I'm going to do here is I'm going to, because I'm running out of room, I'm going to write down that common denominator that I'm going to get, cosine theta times sine theta. So I have the 1 that comes down minus. Now over here, when I create that common denominator and multiply the numerators, I'm going to get sine squared theta. And there's an equal here. Not quite done. Running out of room. Let me come over here. All right, observe this fraction. Notice that the numerator is actually equal to cosine squared theta by the Pythagorean identity. So I'm going to keep that same denominator, cosine theta times sine theta. But in the numerator, I'm going to replace this numerator with cosine squared theta. And I have an equals here. Well, I can divide out cosine theta with one of these cosine thetas up here, leaving us with cosine theta over sine theta with an equals. Okay, and we're lucky because right here this is equal to cotangent of theta, which is what we're trying to get to. All right, so the takeaway from this problem is we did the algebra. It wasn't pretty. We changed to sines and cosines. Nicely, some things canceled. What we were left with were two terms where we could find a common denominator. And then we used another Pythagorean identity substitution so that we could do some more algebra to get to what we needed. Okay, example 3. Definitely, this looks like the more complicated side. I see the pi over 2 minus y. So I kind of immediately begin to think about my formula sheet and those cofunctions. I see a cotangent squared quantity pi over 2 minus y. Let me see if we have any of those squares. We do not. But what I do have is cotangent to the first power of pi over 2 minus u, or in our case, y. All right, and I know that one of them is equal to tangent of u. So what if I made this cotangent squared? Would that allow me to come over here and say that that's equivalent to tangent squared? Yeah, because if you think about what we have here, let's just write it out. I'm going to keep the secant squared y minus, if I have a power of 2 on this cotangent function, that just means that there's 2 of them, times another one, so looking back at your cofunction identities, I can replace that factor with tangent of y times another tangent of y. So let me combine these two. That's going to be tangent squared y. Go to your Pythagorean identities, the ones that we rearranged that are on the bottom of your formula sheet down here. Okay, one of your rearranged identities should have this, and what it's equal to is 1. So this came from your Pythagorean identity that you rearranged. It's another form of 1 plus tangent squared x equals secant squared x. All right, number 4 follows number 3. First thing I notice is I think about cofunctions. This is secant squared, so let's go to your formula sheet, see if we can find secant of quantity pi over 2 minus x. Cofunction identities, secant pi over 2 minus x would equal cosecant of x. But because I have a square, this is going to be cosecant squared x. And then right here, don't forget you have a minus 1 to bring down. Go to your Pythagorean identities right here. Look at this identity that we have, okay? We have rearranged versions of this, like just move the 1 over. Okay, so this right here is cotangent squared x. Okay. Number 5. Well, the left-hand side of the equation, again, is a more complicated side, so I guess we'll work there. Let's look and see what we have. All right, I've got a fraction minus cotangent of theta. I notice that in the fraction, I have a monomial in the denominator. I'm thinking share the love, like we did in number 1 above. We could certainly try that. You could change everything to sines and cosines. It's just that if you took that approach, you're going to have a fraction in the numerator of another fraction here, and it gets kind of complicated. I try and avoid changing to sines and cosines if I'm going to get like complex fractions, you know, fractions inside other fractions. So, but it's always, you know, kind of in my back pocket that I might use that strategy of changing everything to sines and cosines if I don't kind of have a clear picture of something else to do. But I think I'm going to try what we did in number 1. I haven't done this problem that way. So I'm going to go ahead and share the love here. Let's see what happens. And then don't forget your minus cotangent of theta. So our target is cosine of theta. Let's see what happens. Well, let's see. 1 over secant theta does change to cosine of theta. That's kind of helpful because I do need that, which tells me that maybe these two will cancel. Plus, let's go to your formula sheets. Do you see anything on your formula sheet that would tell us what cosecant theta divided by secant theta is? Not on this formula sheet. Not there either. Okay. Well, what do we do? Well, I'm going to use this fraction, or I'm going to take this fraction right here, and I'm going to actually change it to sines and cosines and see if I can get a picture of what's happening here. So I got a fraction bar for this fraction bar. This cosecant will change to 1 over sine theta, and the denominator will change to 1 over cosine theta. And then don't forget to bring down your minus cotangent theta. All right, continuing down, bring down cosine of theta. Now, here I'm going to keep change flip, which means I'm going to bring this to the numerator, denominator to the numerator, and multiply by the reciprocal. So I'm going to end up with 1 over sine theta times, when I reciprocate, I'm going to get cosine of theta over 1. Be careful because this is cosine and this is cotangent. They're so close, it'd be easy to kind of just make a slip of the pencil there. All right, when I multiply these two fractions together, I'm going to get cosine theta over sine theta. Well, cosine theta over sine theta, I do know is cotangent theta. And then don't forget the minus cotangent theta. Those two will now cancel, and I'm left with cosine of theta equals cosine of theta. So on this problem right here, we did the break apart strategy, changed to sines and cosines on some of the terms. I didn't change that to cosine over sine, just because I wanted to see if I could get this to be cotangent to cancel with that. These problems just require some analyzing and some thinking. All right, number 6. More complicated side here. Less complicated here. Let's work on this side. I see 2 terms. Here's a term made up of these 2 factors, and then here's a term. You could factor out a sign if you wanted to. I see that I have a common factor of sine and here and here. I'm just thinking, would factoring out a sign help me? Maybe. Haven't thought about that approach before. Okay, well, what happens if I don't factor out a sign? What's another option? You might know that this multiplication right here, if you did multiply, would be 1. That might be a good thing to think about. So I'm going to work on this term. I'm not going to take out a common factor just yet. If you did and did all the correct trigonometric algebraic work, I'm sure you'd get the same answer. But at this point, I'm going to take sine theta and multiply it by 1 over sine theta here for that cosecant. Because I know those are going to divide out, and I'm going to have 1. And then bring down the minus sine squared theta. So this product becomes 1. And we are 1 step away. 1 minus sine squared theta is a Pythagorean identity. That's equivalent to cosine squared theta, which is exactly what we need. That was probably one of the easiest ones on here. All right, number 7. Whew, looks pretty complicated. This is our longest one too. We're gonna need all this space here. All right. Definitely gonna work on the left side, making it try to look like 2 times cosecant of theta. Which, when you think about this right here, sometimes it's good to do one step on the right-hand side because this isn't real comfortable to us, but this is going to be 2 times 1 over sine theta, or 2 over sine theta. So 2 cosecant theta is equivalent to 2 over sine theta. So if I do some work over here on the left-hand side of the equation and I get to a point where I think, oh, I think I can get this work to be 2 over sine theta, I would be finished. So sometimes, like I said, it helps to kind of do a step or two or a thought process here to kind of see where you might get to over here, and you're well on your way to proving this identity. Okay, number 7. I could definitely share the love on the second fraction here, but I could not share the love on the first fraction because this is not a monomial. We have 2 terms, it's a binomial. So I'm not even sure I'm going to break it apart. If I want to add these 2 fractions, then that's about the only thing I've left. I think I'm going to get a common denominator. All right, so at this point, if I'm going to get a common denominator, I have to multiply the first fraction, the left fraction, by tangent theta over itself. I'm going to go ahead and put parentheses around here. And over here, I need to multiply the second fraction by 1 plus secant theta over itself. And make sure and put these in parentheses. Okay, this is going to be a mess, but let's try and kind of keep it organized. So I've got this plus sign here. I'm going to have a big fraction bar here. Multiplying these 2 fractions, we end up with tangent squared theta over. Now, instead of distributing the tangent theta in, I'm going to leave that common denominator in a factored version. Just like this. And likewise with the second fraction over here, when I get a common denominator, let me leave the denominator in the factored version. Sometimes I do that. I like to leave it factored just in case when I clean up the numerator, I might be able to divide out something since I'm in factored form. All right, let's look at this numerator here. I'm going to multiply 1 plus secant theta times itself, so that requires foiling. So I'm going to FOIL these together, and I'm going to end up with 1 plus a secant theta, another secant theta, that's 2 secant theta, and then the last terms would be secant squared theta. I like seeing that 2 because I know I need a 2 for the answer. All right, let's combine these fractions that have a like denominator. So what can I do from here to up here? Well, look at these first 2 terms here. What do we know about 1 plus tangent squared theta? Well, I do know that 1 plus tangent squared theta is equivalent to secant squared theta. Will that help? Not sure. But these are secant terms, so might as well try and take these and put them together. Rewriting secant squared theta plus, bring over your other 2 terms. Oh, I didn't save myself enough room. Okay, well, I guess the natural thing for me to do next is to collect those 2 terms. So that means I've got 2 secant squared theta terms plus 2 secant theta terms. Now, I can't collect these are not like terms, and then this is all over tangent theta, still 1 plus secant theta. In the numerator, I'm going to take out a common factor of 2 secant theta. When you divide 2 secant theta out from this term, you're left with just a secant theta. Plus, when you divide 2 secant theta out of itself, you're left with 1. And I'll re-record the denominator. Was that helpful? Sure. The numerator and denominator are both factored. I can divide out those common factors. Getting closer. So now I have 2 secant theta divided by tangent theta. Remember, what we want is 2 cosecant theta. So I am gonna, have to come over here. I think I'm gonna take this 2 and just kind of put it out front of secant theta over tangent theta. Secant theta, I'm gonna change to 1 over cosine theta. And tangent theta, the denominator here, is gonna change to sine theta over cosine theta. Here's my new equals. This is just saying 2 times this. I don't want to mess with the 2 just yet. So 2 times what? Well, multiply by the reciprocal. So 2 times 1 over cosine theta times, now change it to cosine theta over sine theta. And there's an equal here. That's lovely because the cosine thetas divide out and I'm left with 2 on top of sine theta. But remember what we did way back up here. We said if we see this, that we know that we have the answer. So you got an equal here, and you can just change this to 2 times cosecant theta. Whew, that one was pretty intense. Okay, but we hung in there. Looking back at it, we decided not to share the love. We decided to get a common denominator, requiring us to multiply the left fraction by tangent theta over itself and the right fraction by 1 plus secant theta over itself. We left the denominators in factored form. We multiplied the numerators together, put the numerators together. Notice that we had 2 secant terms here, and so why not change that to secant squared theta by the Pythagorean identity? Collected like terms, refactored so we could divide out with one of the factors in the denominator. Did some trigonometric substitutions, cleaned it up, and eventually we ended up at our answer. So sometimes proving or verifying trigonometric identities is a quick 1-2 step and you're out, and sometimes it requires perseverance. Thanks for hanging in there.